Hey, are you enjoying this polynomial journey? It's amazing, isn't it, mathematics? We've discovered polynomials, and gee, isn't it developing what we can do as we explore them? So just recapping a bit, done a little bit of squiggling up here, and we can see that we have terms like q of x, d of x, r of x to make up our polynomial. And we've been looking at whether things have factors and remainders and stuff. And just remembering, for this particular one here, I want you to be able to write this dividing through by the divisor. Just remember, the other way of looking at this division algorithm is to divide everything through and say it divided in this many times, and we had a remainder which was like that. That's the other way of expressing the division algorithm there. And there's q of x and d of x for divisor, and the remainder up here, r of x. Okay. And then, of course, sometimes when you do the division by z take 2, maybe you get, it goes exactly and there's no remainder. So you can say, okay, these are factors now. And I guess you look at that quadratic and you'll say, hey, I wonder if there are some complex conjugates hiding in there. Are there any complex zeros if I put this function equal to 0? And of course, just having a look at it, b squared take 4ac, I think is 20, isn't it? So no, there would not be. There'd be two irrational zeros. I hope you're up with all this. So if you're not sure, rewind and just listen to me saying it again and see if you have gathered that knowledge and accumulated that knowledge from the other presentations, the zeros and the factors and all that stuff. And now what we're going to look at are some graphs here. These couple here, have a look at those and see what we think. Well, here we are. We will have some x-intercepts or zeros of this function, and that would be a cubic. Here we've got some zeros. Oh, there's a repeated zero. How is that going to come up in factor land, I wonder? Okay, well, let's go on and ask some questions about these polynomials and delve even deeper into the world of polynomials. Okay, so coming down now, here we are. How could you tell whether an expression has a factor? I've already underlined that, a factor. Okay, no, whether it is a factor, sorry. In other words, if I took x take 1, does that go directly into a polynomial expression? Or x squared take 3x plus 5? Is there any way of telling whether the remainder would be 0 maybe? Because that's what we mean, isn't it? If you have a factor, when you do the process either this way or with synthetic division, x take 1 or 1 coefficients and working it out, we want, and we do this process this way, we want the remainder to be 0 down here. If it's a factor, if x take 1 is an expression which is a factor, we want the remainder to be 0. I wonder if we can find something out about that without doing this division process. Right, come down, let's have a look at something interesting. I'm not sure whether you've noticed this, so I've got this question for you. Have you noticed this? When you divide, let's say, a cubic by x take 2, it will go a certain number of times and then you put the remainder over the divisor. Okay, so that's a process of division. And of course we can write that another way, that this polynomial equals this times x take 2 plus 9 on the end. The two ways of representing the division algorithm. Okay, have you noticed that after you do that, have a look down here, you take the original polynomial and you sub in 2. Now not neg 2, you're dividing by neg 2, but it's the opposite sign. If you take it and put it in place of x in the polynomial everywhere and work it out, you get a value of 9. Hey, that's the remainder. Wow, how did that happen? In other words, if you want to quickly find the remainder for this particular division, rather than going through the whole division process or algorithm, you could take the 2, put it in, and find that, x take 2 is not a factor, doesn't divide exactly, we've actually found the remainder. That could be really powerful, couldn't it? That will shortcut the division process. We might not bother with the division process if we know it's not going to divide in exactly. So we could detect the remainder. Wow. Now this is called inductive reasoning. We found an example. You could do a few more examples, and it looks like we found something. But of course in maths we've got to do a deductive proof. So come down here, and here's a little proof. And this is in the course specifically mentioned. So they could just say a question like, prove the remainder theorem, with no lead up to it. That's the only theorem in the course that is specifically required to be known, or the proof to be known. You could be asked to prove other things, but this is a standard theorem here, that the proof of which should be known. So when polynomial p of x is divided by x take k until a constant remainder, so you can't do any more divisions. So yeah, if you're dividing a quartic by a linear factor, you've got to keep going until there's no x's left. Okay, and just have the remainder. And then they're saying, well, the remainder is equal to what? The value not neg k subbed in, but k subbed into the polynomial. The opposite sign to that constant there, if you like. So let's have a look. Let's take the division algorithm here, that p of x is q of x by x take k, your divisor, plus the remainder, using that form. Okay. And what's the other form? Let's just check now. The other form is, say, that p of x over x take k equals q of x plus r over x take k. That's the other way of explaining the relationship in that division process. Okay, so we've got that statement. We'll give that a tick because that explains the division algorithm. Now let's sub k in and see what happens. So p of k equals, subbing it in everywhere in our expression where you'll see x, and subbing, here's why it works, subbing in k and there you get naught. So when you multiply these two together in evaluating p of k, it goes to 0. Q of k times naught is 0. And so that's r. That's how it works. Now how powerful is that? Just remember now that it's the opposite sign in here. The k has to be of the form x take k. So come down and let's look at an example. Screen clippings here are from Hayes and Harris publications, so it'd be good to grab their specialist book and have a look. So here we are. Use the remainder theorem to find the remainder when this is divided by the linear term x plus 2. So the polynomial, writing it out neatly. Now look at this p of neg 2, because it's got to be x take k. So that implies you've got here x take neg 2 to get the plus 2. See that? So here you're going to sub in neg 2. Watch that. We proved it for a factor of x take k. If it's x plus something, it's a negative value in there. So we're going to stick neg 2 into the polynomial and we get 34. So the remainder is 34 by the remainder theorem, and you could just put remainder theorem RT, but we should refer to it here as the reason for our statement. Pretty powerful stuff. In other words, if we tried to divide this by x plus 2, it would have a remainder hanging off the end of 34. All right, your turn to have a look. And 3.1, there are 5 questions there. So go carefully, think about some of the latter ones here. And you might have a look at a process for division by x take 1, the remainder is 4, divided by x plus 2, remainder is 16. I think we've got 2 unknowns. That suggests 2 equations, doesn't it? Think about that. Okay, pause the presentation, have a go, and you can forward it in a minute as you do each problem and look at the solutions, which are down below. Okay, so I'm going to show you those now. Coming down here, question 1, 2 and 3. Study them carefully. And 4 and 5. Okay, so interesting little puzzle problems there as we build up in polynomial land. Okay, go back and check your work and make sure you understand this, or talk it over with your classmates and your teacher. That's always good. A dialogue approach to maths is good. Okay, so come down now and let's have a look at another little example here. So when p of x is divided by x squared, take 3x plus 7, the quotient is that, and the remainder is unknown. That's interesting. However, when p of x is divided by x, take 2, the remainder is 29. When divided by x plus 1, the remainder is negative 16. If the remainder has the form ax plus b, find a and b. Well, it would have the form ax plus b in most general terms, wouldn't it? Because here we're dividing by a quadratic. So once you get to a linear term, ax plus b, it won't go anymore. Now, it might not have an x term left over. It might just have a b, but this is the most general statement of the remainder. So it's going to be 1 degree less than I nearly put the quotient, than the divisor. Once you have just x's left, you can't divide anymore. So you might have a term ax plus b left at the end of your division process. So you must write down the most general form for the remainder, and here it is, the division algorithm, x squared plus x, take 1, that's the number of times it went, lots of d of x plus the remainder, using that form. Now you might have already guessed, we've been given two things, and that is the remainder on division by x take 2, and that's 29, so that means p of 2 is 29, subbing it in, there we are, subbing it in there, has to equal 29, and the other one has to equal, subbing in neg 1 for the division of x plus 1. Remember, x plus 1 is treated as x take k, x take neg 1, so that's your k value in this context. So subbing it in, we get equation 1 and equation 2, and then simplifying them, and then using, substitution or elimination. You could take these equations away and get rid of the b's, or you could use technology, graphics display calculator. Okay, on the Casio 9860 Plus great calculator, you would use Equimode. Okay, and all the calculators have a similar mode for solution of simultaneous equations, and therefore you have the two answers there. All right, so little tricky do's there. Just remember this statement here, which comes from the division algorithm. You must be aware of that. And that's back on the first screen, of course. All right, come down and it's your turn and see what you think. Got a few little problems here. A couple of hard ones at the end. You'll have to look carefully at the solutions of those and see how far you got with them. Remember, you start with that division algorithm, put in pieces of information, and just make sure you use all pieces of information as you go along. All right, so pause the presentation and see what you can do. Remember, starting with a statement of that division process. P of x equals q of x by the divisor plus a remainder, where the degree of your remainder is, to be completely general, 1 less than the degree of the divisor. So if we're dividing by a quadratic, you've got to have ax plus b in that r of x whole. Okay, pause it, have a go. I'll show you the answers now. Coming down, let's have a look at questions 6 and 7. Questions 6 and 7. And then in question 8 and a bit of question 9, so there's question 8 there. Interesting little one, you've got to shuffle some terms around up here. And it's a little bit of algebra, more than polynomial understanding of how to shuffle the terms around so you can solve. Then in 9, there we have question 9. Please note here the generalization of the remainder, because you're dividing by a quadratic, effectively repeated linear term there, multiplied together, then the remainder could have an x still in it, and you must have that general ex plus f there. All right, are you enjoying yourself? It's moving quite quickly, isn't it? Let's go to the factor theorem. This is really just a consequence of the remainder theorem. So it's saying k is a zero of the polynomial implies x take k as a factor, and vice versa. Okay, if and only if, or double implication, this implies that. If it's a 0, it means x take k will be a factor. If x take k is a factor, it must be a 0 of the polynomial. We're trying to prove that now. So a 0 of p of x implies p of k must be 0, and vice versa. This is sometimes stated if, with a double f, meaning if and only if. So it's a double implication sign. One implies the other, both ways. So now that would imply that the remainder is 0. Therefore, the polynomial can be written as q of x times x take k and no remainder from the division process, the division algorithm statement. Therefore, x take k is a factor. So there's a little proof of the factor theorem. And it goes vice versa, means a double implication sign. One implies the other, and backwards. Okay, so I think we sort of knew that from before, but there's a formal proof of it. So we can actually talk about how to create factors from zeros of a polynomial. So that's going to be important to find those factors now. So come down and have a look here. Okay, find k given that x take 2 is a factor of this thing here. Then fully factorise it. Okay. X take 2 is a factor. So we can say by the remainder theorem or the factor theorem, p of 2 is 0. If that's a factor, then it's also x equals 2 is a 0. So we can call it the factor theorem here. So subbing it into the polynomial, the x value of 2, we get k equals -2. Okay, so we know it's a 0, so there it is, and solving for k equals -2. All right, so now fully factorise this. Well, we've got our k value in place now, so we can say we know there's a factor. There's an undetermined factor here from our last work. That's got to be a quadratic to get this cubic up here. So this is a general quadratic. And you might say, well, Huddy, you've put some things in here. It's not particularly general, the 3 and the x squared. Aha, but we know that, don't we? This has got to be x squared to produce the x cubed term. This has got to be -3 to produce the 6 here. So we don't overgeneralise it. There's only necessary for one undetermined coefficient. I only need one of them. The first and the last terms we can suss out from FOIL, from expansion of those brackets. All right, so now we will equate coefficients. So the x squared here, x squared term is -2. It's got to be equal to -2 plus a. So they haven't shown the expansion here of multiplying that all out. So maybe I'll just do that. We'll have x cubed plus ax squared take 3x. Let's just put this on this. -2x squared take 2ax plus 6. So this is what they're talking about here. The x squared term is a take 2. The x term is -3 take 2a. There it is there. So this is the x squared coefficient, and that's the x coefficient. So they've left this expansion out and just plucked out the two coefficients from over here from the expansion. All right, so it checks in both cases that a is 0. And so therefore we can say that the fully factorised here is x take 2 by x squared take 3. All right, now down here we've got an alternative way using synthetic division, which is actually not in the course, but you could do it. You could divide the original term, original polynomial by x take 2 and get these, that's the quotient, and that's the remainder. Okay, so the quotient is going to give you the other factor, which is this thing here, and you put k as -2, and therefore get the other factor. It's quite neat, but not required in the course, so please yourself whether you take that on board. But there we have done it. We have done that factorisation, but fully factorised would suggest that you have linear factors there. So x squared take 3 has to be looked at as x squared take here 3i squared. Yeah, so here there's going to be x plus I root 3, x take I root 3. Alright, so have a look at that and make sure you're happy with that. That's picking up on some stuff from the last presentation on factors, zeros and what else, roots. That's right. Alright, let's go down and give you a go trying to put those processes together. So I suggest doing all of these just to keep the skills up. So pause the presentation and have a go. Right, I'll show you the answers now. Well, here we are. Question 1A and B. And they've done it with synthetic division, so that's a bit disappointing. Okay, because that actually is not in the course. Okay, so you might check your answers there using substitution and then using the idea of undetermined coefficients, constructing of that other factor. All right, let's go down to question 2. There's the rest of 1 and 2. All right, we're getting some skills up, aren't we? So you might have to go back and check. Let's go on and have a look at what other things we can do. So if we know a 0 of a polynomial, here it is here, hence find k and all the other zeros. Since 2 is a 0, then p of 2 is 0. So we could put that equal to 0 and find the two values when we sub it in. Now, with synthetic division here, you've actually got a bit of advantage because you can put that equal to 0, but you also have automatically, because you've used synthetic division, the quotient. So you know that other factor here. Okay, so you want, if 2 is a 0, then you know the k values, take it 0, and you can put that into here to actually do it. There's two different ones here though, -5 or 3, so that's the factor if it's -5, and this is the factor if it's -3. And then you can find all the other zeros from those factors. So the alternative to that, in this case, is to say z take 2 is a factor, and therefore you've got z squared plus az, and what would the other factor be to give us our polynomial. Okay, so it's not going to be easily done in that way here, to do it with undetermined coefficients, okay, because we don't have easy numbers down the end. So that's why they've gone synthetic division. So the other way of doing it might be if you do z take 2 and then z cubed and go through a bit harder, do z squared plus k take 4, z plus k squared take 23. So it's a little bit messier. But just remember, you're not expected to do synthetic division. So it is neater than this one here, because you're going to have to go through and do our long division process. Okay, and keep bringing things down and so on. So it's a little bit longer because you're going to have k's in it and be able to put, and you come up with this at the end and put equal 0. Same idea, but it looks a little bit more untidy that way. There's only two ways. The undetermined coefficients can't really be used easily in this one. Okay, so remember when you get that other factor, don't forget you want the zeros, so you've got to put the other factor equal to 0, and that's a quadratic, and so you're going to get 2 from that and 1 0 from z take 2. So a bit disappointing there that they've gone for synthetic division, so take your choice. Are you going to learn synthetic division or just stay with what's in the course? So that's up to you. Let's go down and see if you can practice some of this stuff. Here we are. 3, 4 and 5. So again, some messy creatures here on the end. And see what you think. Trying it with long division and equating the remainder to 0, seeing what the polynomial is if for the two values when the remainder is 0, and so on. So try to consolidate that. All right, I'm going to show you the answers now, so pause it and have a go at one question, go and look at the answer, then go on. Don't do them all and find they're all wrong. Don't perpetuate an error. Okay, let's go down and have a look at the solutions. Okay, question 3. Again, they've done syntactic division. Just make sure if you're doing long division here that that's your remainder and there's your quotient up the top, and then you proceed in the same way. Putting the remainder equal to 0, getting the 2k's and creating the two quotient expressions there. All right, I'll show you question 4 now. Question 4. And question 5. Okay, let's go on and see what you think. So the second part of this, as you know, was remainder theorem. That's a nice little theorem for leading on to the factor theorem, if you like, for detecting whether you've got a remainder. And now we're going to use those things that we've found, the zeros in other words, to the zeros of the functions, to graph them. So we're going to graph cubics for a start. So here, Hayes and Harris have got this little investigation, so you might do it from the textbook. And it's saying you've got 4 types of cubic. You've got one where you've got 3 linear factors, and you're going to generalise all of them by putting that scalar out the front. So you've got that multiple of it, because any polynomial of that form would all have those 3 zeros. Or you could have a repeated zero. What happens there? So this would be, what, 3 distinct x-intercepts. I think you know from quadratic theory that this is going to give you a touching point on the x-axis. Could you prove that? So we've got 1 intercept and 1 point of touching on the x-axis where you have this repeated zero. And then one where you've only got 1 linear zero, 1 linear factor, the other's a quadratic, and this is got a negative discriminant, so hiding in here is a conjugate pair. So that's going to have what? No x-intercepts. No x-intercepts coming from that part. So we'll just have the 1 x-intercept coming from that factor there, x is alpha. And then this one's interesting. The x take a all cubed, 3 linear factors, all x take alpha. And so that's going to be reminiscent of what? X cubed, which has 0 as its x-intercept. So if you translate that, alpha in the x direction, then x take alpha cubed is going to give you the 3 factors, and it's just going to be a point of inflection. As we do calculus later on, or if you've done calculus in another subject, it's a point of inflection there. A stationary point, but not a turning point. All right, let's go down and summarise that now. And I think it's probably worthwhile writing this down as a set of notes. So if alpha is greater than 0, so that means the a is greater than 0, so that means the leading term, the x cubed term, will be positive. So what's that going to do? It's going to be for large x, it's going to end up upwards and downwards there. For large x, out here, it'll be x cubed. And if this is positive, and you go for large positive x, then x cubed is going to be positive, a is going to be positive, it's going to go up. The two ends are going to be opposite. For large x, it's going to be up. If a is less than 0, x by x by x is x cubed. For large x out here will be positive, but multiplied by a is the negative in front, it will go down. So it's either going to have those 3 intercepts and go down, or point of inflection and go down. So the idea is that the behaviour of a polynomial is really controlled by that leading term, isn't it? Because as x gets very, very big, these other terms slide into insignificance. And the controlling term for values high up for x, as x tends to a positive infinity or negative infinity, are determined by this. Give you an idea, x cubed, if x is 1,000 x cubed is 10 to the 9th. X squared is 10 to the 6th. See the idea? So here, for example, this is 1,000 times that. So therefore this becomes insignificant. This is going to be far greater than the value of the leading term. So all you need to look at for large x, either tending to positive infinity or negative infinity, is the sign and the behaviour of that leading term, because the others will be wiped out by its size, if you like. So think about that. Okay, so here's a cubic. 3 linear factors. The graph has 3 distinct intercepts, you know that. And the graph crosses over or cuts the x-axis at these points. Okay, and here's the repeated one. Graph touches at alpha and cuts it at beta. We've talked about this. And this one here, this is if b squared take 4ac is less than 0, the graph cuts the x-axis there. The imaginary zeros do not show up on a real graph, because what we're plotting is on the Cartesian coordinate system is x and y values which are real. So you can't plot those complex conjugate. Remember, these will be conjugates in here too. The imaginary zeros will occur as a conjugate pair. That's how they're hiding within these coefficients, which are real, because the sum and product of a conjugate pair are both real. So just remember that idea. Don't forget stuff. Accumulate knowledge in maths. That's very important. Okay, so they don't show up on the real Cartesian plane there. For a cubic of this form, okay, so it's 3 linear factors all the same. It has intercept alpha, and at alpha the tangent is horizontal and crosses over the curve at alpha. So the idea is that that's a stationary point, either like that or like that. If A out the front is positive, for large x therefore, it would be going up. If A out the front is less than 0, for large x the leading term will be negative, will be positive, and this will multiply it by a negative, which will mean it will be going down in the negative region. Okay, so but this is what we're talking about. A repeated linear factor, or repeated 3 times, it's going to give a stationary point there, which is a point of inflection, not turning around point. Okay, not a turning point. And all cubics are continuous smooth curves, because we're talking about real real polynomials here, and they're continuous functions. There's no asymptotes and that stuff. Okay, let's go down and do something. All right, so we're starting the graphing section now. Find the equation of the cubic with graph that or graph that. And these are the two I showed on the first screen. So you go through, you find the intercepts, and therefore you say the form of the cubic will be, don't forget to generalise it. It must have these 3 factors to produce those intercepts by the null factor law. When you put this function equal to 0, put each of the factors equal to 0, and so you get those zeros. So that's the idea from the last presentation, roots, zeros and factors. But don't forget there's a whole family there, different steepnesses. If you put an A in front, these pieces will all be different steepnesses. Let's just try to draw one. And so here, what could we do? We could draw this going through 8, and let's see if I can do this. So you could have different steepnesses all going through those same intercepts. So let's see if that's the idea of A. So here, but we've got to pick up the idea that this goes through -8. So therefore, when x is 0, sub in 0 in these spots, and you must get -8. So A is -1 here. Okay, so that's the idea here. So depending upon what the y-intercept is, that locates the graph. Just note that it's going to be negative in front, which means when you expand this leading term, x cubed, you'll get neg x cubed. And so therefore for large x, it's going to go down. For large positive x, if I sub in x tending to positive infinity in there, the x cubed is going to be positive. That's going to be a negative in front, so it's going to go down. And opposite the other end, so just check that. Okay, so here, touching to that indicates a squared term. This is the neatest way of doing it. X take 2/3 makes sense also, but it's easier to put it like that. So do that, and x-intercept here of -3 means it's like that. Don't forget to generalise it. Could be a whole family, different steepnesses. What member of the family is it? Well, when x is 0, y is 6. So here you've got the value -2, putting in, sorry, hang on, let's have a look here. When x is 0, putting in 0 in here, so you get the value -2, and x is 0 in there. So that's got to give you the y-intercept, so that gives you 6. So a is a half. Okay. So this y-intercept in those cases will allow you to detect the steepness of the graph, and therefore the particular family member. All right, let's just check this one. So when you square, that'll be 9x squared times x is 9x cubed, and if you multiply that by a positive and look at the tendency as x tends to positive infinity, the x cubed term is going to be 9x cubed, and that's going to be positive for large positive x. Then you multiply it by a positive, so out this end come up here, as x tends to infinity, yes, it will keep going up positively. Can you see that? You can inspect the leading term in the polynomial. Okay, so that'll be a times whatever the x cubed term is, and that's going to control the ultimate behaviour of the function for large x, either that way or that way. And the ends are going to be opposite, of course, because x is cubed, and for large positive x, that's going to give a positive. For large negative x, it's going to give a negative. So the ends are going to be opposite here. How much maths, how deep do you want to go into this? We're going up Huddy's hierarchy here, say, hey, I see it. I actually can do the work, I've got the concept, and I can see why it all happens. That's what you want to do. Get up close and personal with maths. That's when it's fun. Okay, come down. Let's have some fun with these then. Let's have a look. What we've got here is a bit of a summary. If you're given this sort of function, you'd know from this that x take 3 squared, and you should always put the most general form there, ax plus b. You could put a there and x plus b there, but it gets a bit more messy when you're doing the algebra. So as we did with the remainder back in the earlier presentations, call that ax plus b, incorporate your a in that position, it's easier to work with. And here, of course, if you're given functions of this form, there's only one x-intercept, and oh, that's 1, so this should be really x take 1, shouldn't it? Didn't notice that before from the textbook there. And then the most general form will be ax squared plus bx plus c. Put the a in front there, not out the front here. That's the easiest way of dealing with those when you're going to work with them. Right, come down and let's do some work with them. So 3F1 here, you're trying to just explain the idea here from the summary notes up the top, then matching or finding the equation of the cubic in general terms. Don't forget, generalise with an a out the front, whatever you're going to do. Okay, so have a go at those. I'll just show you the others now. Oh, sorry, here's the answers. So have a look. Question 1 and then 2 down to C. Okay. Okay. Very good. Just noticing, I haven't mentioned this, we should say A is not equal to 0 in the following polynomial. When we make the statement of the final polynomial, we should say A is not equal to 0, because if A is 0, there is nothing, of course. Y is 0, this is the x-axis, so we should actually put that proviso. I omitted to say that. Okay, let's keep going now and see what we can come up with here. Another cubic, we've got these x-intercepts and passes through point 1, neg 40. We'll construct it, don't forget the A, and here Don't forget A is not equal to 0, I left that out before. If A equals 0, of course, the whole right-hand side is 0, and that's the x-axis. So there's no polynomial work to be done if we do that. So we're saying that, and then we're given that the point 1 neg 40 is on it, so subbing in 1 into the 3 positions of x in the function gives us neg 40, so A is 2. So there's our final polynomial that fits this specific and unique case. This is a unique polynomial now because we've got the general result, but we've got fixed it with a particular point on it. Can you see that? It's no longer a family. We've plucked out the particular family member that goes through that point. All right, come and do some. So here we are. I'll just bring this up. I think I can get it all on. I think that's the way I did it. No, I can't. So find the equation of that cubic, question 3. And you can pause it in a minute and have a go. And then I'm coming down to question 4. And now it fits. Just match the given graphs to the corresponding cubic. Be careful. Some are a bit like each other. So be careful there. So pause it and have a go. I'll show you the last one there, question 5. There. Okay. Let's have a look at the answers. Oh, the boat's a bit rocky here. It's starting to slop over to one side. Okay. Try to keep your feet. And, oh, we've been hit by a wave on the other side. Look at, oh, it's all slipping over. I'm sorry about that. Hope you're not getting seasick. Let's have a look at the last bit. In C. Okay, so how are you going? Study all those. I think it's fairly straightforward. Just got to watch the algebra that you're doing the right thing at various stages. All right, let's go on a little bit now with quartics, power degree 4. Okay, we'll just come up here a little bit. Yeah. We're going to do the same sort of thing. Here, if A is greater than 0, the coefficient of x to the 4th, we're talking about this sort of thing here, a degree 4. So if A is greater than 0, the graph opens upwards. If A is less than 0, the graph opens downwards. Would you please notice here that both the ends are the same because of even degree. Let's just check that. As x tends to positive infinity, x to the 4th will be greater than 0. And as x tends to negative infinity, because it's an even power, that will also be greater than 0. Unlike a cubic, with the cubic term, if x is greater than, if x tends to positive infinity, x cubed will be positive. As x tends to neg infinity, x cubed will be negative. So the ends of a cubic oppose each other. They're opposite. But the ends of a quartic, which is even power, will be the same. They'll both be opening upwards or downwards. So think about the mass behind that. That's important. And so we still have to look at the effect of that generalised A out the front, because it's going to determine the direction. So here we are. If it's greater than 0, it's going to open upwards. Less than 0, it's going to apply negative and open downwards. So here we are. If we had a single factor, what does the graph of the function look like? Then a single factor x take alpha, the graph cuts the x-axis at alpha. So there we have there, and you could look at these other points as well. Each single factor here, the graph cuts the axis at alpha, and as we go on though, let's have a look. A squared factor means you'll have that. A cubic factor means you're going to have this touching point, so it's cubed, so that's going to be our point of inflection. And then the quadruple factor just touches. So these two would have other zeros at the other linear factors there as well. We're talking about just these special conditions. A squared is a point of touching and so on. So very similar idea. Please note this one, where it's quadrupled, it's a flattening there at that point. Okay, here we go. If a quartic with A greater than 0 has one real quadratic factor with discriminant less than naught, we could have that. So if it's a quartic and one real quadratic factor, it's got two linears, so there we are. They will cut, but the rest of this will not produce any more zeros, because the other quadratic factor would be, or this real quadratic factor would have discriminant less than naught. It would have a complex conjugate in there. Conjugate pair, still giving real coefficients because the sum and product of the roots are real, but it won't give any intercepts. So just watch that there. Okay, and a quartic with two real quadratic factors, both with a discriminant less than naught, might look like this, because each of the quadratic factors produces a conjugate pair, a complex conjugate pair, and on the real Cartesian plane you can't plot complex numbers. So although there are two real quadratic factors, there are four imaginary zeros which don't appear. So it actually doesn't cut the x-axis. Okay, so interesting, isn't it? And you can start to see, now think about Hutty's hierarchy here. We've got some algorithms that we're doing. Methods of solution is an algorithm. But what's the concept? What's the idea? Okay, and that's, you know, learning these things off, I suppose, about the zeros. And the I see it level, which I want you to get up to, hey, I actually get that. I want to get up close and personal with the maths. I see it is really when you say, well, ax cubed, do you see, that's going to, the growth of that's going to outstrip all these other terms. So it's got a controlling influence, and we can look at what happens to x cubed for large positive and negative x, and what what the sign of A is, and therefore deduce what it's going to do. So that's the level of I really get it, rather than just going through the rules. Okay, so try to come up the hierarchy of learning in maths. Get up close and personal with it. Okay, let's do that. Let's come down now and have a look at these. So we're going to go through the same sort of process. Find the equation of the quartic. So we're going to say it touches there, intersects there and there. So we'll put an A out the front, generalise it, repeated zero for neg 1, therefore x plus 1 squared, because it's touching, and then the other ones, and we should say A is not equal to naught here. We don't have to, because we're going to go on and particularize it. See, we've got a particular point on that family. So here we've got when x is naught, y is neg 3, the y-intercept. So putting in neg 3 and putting x into the three factors, and we can particularize and make the solution unique, because we actually have a fixed unique point on it. Here we have cuts it there, cuts it there, cuts it there, and cuts it there. So here A outside of x plus 2, x plus 1. Notice this, instead of negative half, we can write 2x plus 1. Instead of 3 over 2, 2x take 3. A neater way. Okay, and then do we have a particular point? Yes, x is naught, y is 6, the y-intercept. So putting 6 and then subbing in naught into the x positions in each of those, and we can get our quartic. All right, your turn. Come down and have a go. Question 1. I'll have the answers down below as usual. I do all of these. Let's go to question 2. Matching up. Okay, have a go. I think that's probably going to give you a good insight. Here are some answers. Oh, the boat's been hit on the other side again. It's rocked away. I hope you're not getting seasick there. Okay, answers to question 1. Let's go to question 2. Okay, and we'll finish off. Just a little bit more to do here. I hope you're putting all this together in your mind. Okay, quadratic touches x-axis at 2, cuts at neg 3, passes through these 2 points. Okay, that's a factor because x take 2 squares is a factor because it touches. This is a factor because it cuts, and therefore we've got those two. Now we need to construct an undetermined factor here because it's a quartic, and if you look here, squaring that'll give you a square, times by x will be a cube, so there'll be another linear factor. So we're going to use that idea of undetermined coefficients here now. And so subbing in 1, you have to equate it to -12. So subbing in 1 into all these positions, getting -12, we've got one equation in two unknowns. That's why we need this other piece of given information. Subbing x is 3 in and putting equal to 6, we'll get another equation and we can solve. So it was pretty predictable when we got to here that we did need the 2 points from up here. So start to think about it. Two unknowns in the problem means we need two pieces of information, generate two equations, and then solving them simultaneously, either by elimination, substitution, or technology, equimode on the Casio 9860 Plus. Okay, and then we can put that final undetermined factor together. Right, a little bit tricky. Have a go at these, and we'll finish up. Questions 3 and 4. Pause the presentation and try to work through those techniques. Just remember here, half, 2x take 1, 2x plus 1, those sorts of things. And fractions here, don't use fraction, gets messy. So here, 2x take 3, that sort of thing. Okay, let's have a look at the answers. There's question 3, A, B, C and D. Oops, just fit in that last little bit there for D. And then finally question 4. All right, and that's the end of that one. And we're nearly at the end of polynomials. I hope you see the explosions happening. It's really good stuff, this polynomial algebra. So I think one more presentation and we'll wrap up polynomials. So I'll see you then. Cheers for now.